Do you go by Sammy ever?
Depends on who's talking to me.
Okay. Greetings and welcome, Sammy and Sams of all ages, Samuels and Samuels. Today we're talking about continuity and behavior and this awesome word, monotonicity. Well, it's probably pronounced more like monotonicity, but it's from the word monotonic, which, man, I can't wait to get into that. But actually, we might wait to get into that because we might wait till tomorrow or the next video, which might just be a finger click away for you. How wonderful. But don't hurt your finger because I know you're sponsored, by a fingerboarding company. First of all, regarding continuity, let's talk about discontinuity.
I know.
Disc on tin. Why? Discontinuity. Means infinite discontinuity means that the absolute value of the function or the y value becomes greater and greater as the graph approaches a given x value. So here's the graph of a rational equation, and you see that it is asymptotic, is perhaps what you would have thought of that back in the day. Right? And right, and the problem is that it goes off to infinity and then it comes back down from infinity. But it wasn't like it was connected. It wasn't like there was like a little roller coaster here, It never did that. It literally just went off to infinity and came back down. And it never existed at zero. So this is discontinuous infinitely at that point because it went off to infinity. Sometimes infinite discontinuities also might come back down from negative infinity, almost as though it was like the video game Portal where there was one portal here and then one portal up here and it went whoop, whoop, right? However, that's not actually what occurred. Well, I don't know. Maybe it is what occurs. Maybe mathematicians just haven't discovered the blue and orange portals hidden way out at really big numbers there. So, jump discontinuity. We're going to spend quite a bit more time with these guys. Indicates that the graph stops at a given value of the domain and then begins again at a different range value for the same value of the domain. So notice that it was up here and then suddenly whoop, blip, and then you can actually even have a completely different graph. This, by the way, might be the first time you've seen a function like this. A function that conditionally exists depending on some restricted domain values. This, by the way, if I can spell it, is a piecewise function. I don't know if you've ever heard of those before. And it doesn't just have to have two pieces. Piecewise functions can actually have 3 pieces or 10 pieces. And you can have all sorts of weird behavior. Here, half of it's a parabola, the other half is a line. And just because it's a piecewise function actually doesn't imply that it would have to be discontinuous. Because if this plus 1 wasn't here, then it would have just been a parabola going from this point. And it would have been continuous. And we'll talk about what continuity means in just a moment. Right, my friends? My Facebook non-friends? So, point discontinuity. We might recall this from a previous class you've taken with me when I talked about rational functions. The reason this happens here is x squared minus 1 factors, like so. And if you wanted to kind of cancel this out and this out, you would end up getting the graph of x minus 1, which is the equation of a line with a slope of 1 and a y-intercept at negative 1. And the problem is it looks like that line all the time, except it doesn't exist when x is negative 1. Why is that? Because if x is negative 1, what happens over here?
0.
I get a 0 in the denominator, which is undefined. So it's a restricted domain from the original function, and just because this looks simpler doesn't mean that the domain is no longer restricted. So the domain is still the set of all x such that x cannot equal negative 1 is what's going on there. So what you have is a graph that looks like a regular graph. It just has a little hole in the middle of it, like so. So continuity, continuous. What do I mean by that? A function is continuous if it is not discontinuous. Super helpful definition. The layman's definition is that you can draw it without lifting your pencil. I'll just write that. Draw without lifting.
You can draw that out.
the pencil. How? Oh, I guess like go in the loop around the circle. Well, technically this dot isn't part of the graph. It's just there to indicate that the graph does not exist there. So it's kind of more like a, whoa, 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 look out everybody. Careful, there's a hole right here. Like that's what that is. Like that's like, I should have put caution tape around that circle, like not a circle of the same color maybe. But, although mathematicians just do exactly what was done here. So, so the idea of a continuous function is, right, any graph that I could draw, whoop, 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 right, without lifting my pencil. Like it's a smooth curve, although actually in terms of the piecewise function, it could have even been like this, right, ladies, friends, and like this, right? This would even be continuous because I could have drawn that part all without lifting the pencil. So the continuity test, you guys are going to have to be familiar with this. Familiar enough that you have it memorized, perhaps, is exactly what you have to do. So the continuity test, a function is continuous at x equals c, so at a particular x value. If it satisfies the following conditions. 1, the function is defined at c, meaning f of c exists. There's a y value for that x value. 2, the function approaches the same y value on the left and the right sides of that x value. Okay, that's 2. And then 3, the y value that the function approaches from each side, the left and right, is in agreement with this. It's the same exact thing. So let's talk about what this would look like. So we're going to do our first example here. Oh, so lovely. I'm so excited. It's okay. It's okay. Those trees gave their lives so that you could have an education.
Well, it's Friday. We shouldn't have an education Friday.
So, here we go. Test for continuity, and I'm going to show you this little graph. You could draw a quick little sketch of it, perhaps, or whoop, 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 whoop. All right, so here's a piecewise function. I don't even know what this equation is, but it doesn't matter. I can actually determine continuity nonetheless. So let's first figure out continuity at x equals -1. Yeah, a quick little sketch maybe, or I don't know. We'll see. I'll wait. We'll have our internet friends hang out for a moment while you draw it. Ba, 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 da, ba, 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 da, ba, 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 da, ba. Do, 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 do. Man, I'm excited about this continuity test. Continuous.
I feel like not continuous.
But perhaps that's a very good instinct. But I'd want to know where it failed the continuity test. So that's what we're going to be practicing mostly. Question: would it have been? Is it continuous at x equals -2? Yeah, because the function exists right here. It's approaching the same value from the left and the right, and the value that it's approaching from both sides is the same as the y value that it has where it exists there. Because that's where the function went. So it doesn't exist here, it exists right there. So that's part of the graph. So at x equals 1, let's do the continuity test. So I've got 3 parts, 1, 2, and 3. So part 1, what was the question? Does it exist at x equals -1? What is f of -1, Sam? What's the value when x is -1 here? No, it doesn't exist there at -1. It exists right here. That's why the dot's filled in. So yes, it passes this part of the continuity test because f of -1 is equal to -1 in this case. Right? So a filled circle indicates that the graph exists there. Okay, next question. Part 2 of the continuity test, does it approach the same value from the left and right as it approaches x equals -1? Let's see, as I approach x equals -1 from the left, it appears as though it's approaching -2. And as I approach it from the right, it appears that it's approaching -1. So it fails part 2 of the continuity test. And if it fails part 2 of the continuity test, that means it's actually going to fail part 3, because part 3 was, does it approach, is the value that it approaches from both sides the same as the y value that it has at that point? And it doesn't even approach, so it's just no, because 2 was a failure. So no by default.
Now, is there going to be one where 2's a failure and 3 still works?
That won't be possible. But could 2 work? Well, 3 doesn't. Well, let's find out at x equals 1. Ooh. So, for x equals 1, first of all, question, does it exist when x equals 1?
Yes.
Yes. What is f of 1 equal to here? -1, right? That's when I plug in 1, I get this value right here. Okay? Does it approach the same value from left and right? So let's see, from the left, as it approaches that, it's approaching +1. From the right, it's approaching +1. So yes, right, it approaches 1. So you guys, are both of these arrows pointing at each other?
Yeah.
Like they're pointing at the same thing. Right, well the question, let's read this again. The function approaches the same y value on the left and right sides of x equals c. So the question is, we kind of analyze this graph now. Does it approach the same value from the left and the right? From the left it's approaching 1, from the right it's approaching 1. They're approaching 1, the same value, so yes, it passes that part of the continuity test.
Sure, but why is 1 yes still? I don't get why.
Did it exist at this point? It did. It existed down here.
When x equals 1.
So when I plug in 1, this is the 1. Don't let the tick marks throw you off. Those are halfway tick marks. So when x is 1, y was -1.
Okay.
So that's what that point meant. And then part 3 was, is the value that it approaches from left to right the same as the value that exists there? No. No. Right? If this dot was up here and it was filled in, then yes, it would have been continuous at that point. No, because 1 is not equal to -1. All right, so that's how you would apply the continuity test right there. Let's try another example of this continuity test. I think I've got room for it. I'm going to do it on this side here. So test for continuity, this time at x equals -1 and at x equals 0. Let's see, can I fit this? Oh dear, blast! Let's see, can I full screen over here to get a nice snapshot? Oh, there we go. Giving you guys the best quality graphics here. So, here we are. Yeah, so I'll let you guys catch up drawing this here. So this is a rational function. You've seen these before back in Chapter 9 of Math 3. Horizontal and vertical asymptotes going on.
So the dotted lines are asymptotes?
Yes, so it doesn't exist there. The dotted lines you could pretend are caution tape that trail all the way to infinity. Good times, good times. So, test for continuity at x equals -1. So at x equals -1. And for your homework tonight, I actually want to see like your results for each test. Don't just be like, It's continuous. Like, come on. You know what I'm saying. So, at x equals -1, does it exist at -1? No. Because f of -1 is undefined. Does it point at the same thing from both sides? So let's see. This is approaching infinity. This is approaching -infinity. No. Although, to clarify, even if, like if I was testing continuity here, this would have failed part 1. This also would have failed part 2. I don't consider infinity the same thing that it's pointing at from both sides. Because it's not approaching a value. It's not approaching a number. Infinity is more of like a concept. And right, it approaches the same y value. So I can't think of infinity that way. So this would have failed part 2 even if both of these were approaching infinity. Still would have failed part 2. So I'll just write infinity is not equal to infinity is not equal to -infinity. Yeah, just to clarify that even if they were both pointing the same way.
That's clarifying.
Just to clarify.
Just to clarify, yes, excellent. And then part 3 is just going to be no by default, right? Like, no, right?
So basically what you're asking us to do is not just write continuous or non-continuous, but put no, yes, no.
And some of your justifications, right? Because I want you to do each part of the continuity test.
We have a 50% chance.
Well, you have to give me your justification. Yeah, that's true. Also true. Good time. So, x equals 0.
So that means I'm gonna.
Question, friends. Let's stop complaining. Let's start the learning. So, does it exist at x equals 0?
Yes.
Yes. And f of 0 is equal to 0 in this case. Part 2 of the continuity test. Does it approach the same value from left and right? Yes, it's approaching that. It's approaching that. They're both approaching 0, so yes. Right, they're approaching 0. And is the value they approach from left and right the same as the value that it actually is at 0? Yes, because these are the same. So good news, friends. It's continuous here
Here.
at x equals 0. So the graph itself is not continuous.
All right.
It's not a continuous function, but it is continuous at this point. So I'm just like, I mean, it's kind of like I'm looking for the good in somebody here. It's like, hey, you know, they were pretty good at that one spot there.
You need to have 3 yeses in order for it to be continuous.
Yep. And that is the continuity test. So step 1, it's defined, it exists there. Step 2, both sides approach the same number. Step 3, the number that both sides approach is the same as the thing from step 1. So let's actually let's do one last example. Actually, you know what? I'm going to end this video here. I'm going to save end behavior for the next lesson and monotonic for that. So guys, you could consider this some sort of like Friday long weekend miracle. Hooray! All right, bye internet friends.